So this morning we learned about how shearing boxes are used to study the magneto rotational instability. Although there are many problems and issues about the shearing box, I want to convince you today that the shearing box may hold a key for us to do realistic accretion disk simulations. And I will convince you by going through this multi-scale approach. So because most of us think in terms of coordinate space instead of spectral space, so let me start with something really simple. Throughout this whole talk, you will see I plot the x-axis as the wave number and the y-axis as the energy spectral. EK here is defined that if you integrate EK over K, you get the energy, which could be, say, in hydrodynamics, the Fourier transform of the velocity squared times K squared, because you need to integrate a shell in the K space, or it can be just your arbitrary function, the power spectrum of that. And say, now if we consider the airflow in this room, we know in the really small scale we have thermal fluctuation. And then for long range, we do not have anything up to about a meter. Then there's motion because of my movement. So we get some energy here. Now, the beauty of statistical mechanics is, of course, you can throw away all of this and make things easy. And because there are not too many degrees of freedom right here, so we can either solve this hydrodynamic problem by hand or by simulation. So let me show you a really simple simulation here with different numerical methods. This is by spectral method, which means you just Fourier transform your function pair with the coefficients. This is first order numerical scheme. This is a little bit higher resolution, and this is central difference. So let's take the Fourier transform of this numerical solution. Sorry about that. We can actually see the first order scheme, they are diffusive. They keep killing your high frequency modes. The central difference scheme is not diffusive, but it's dispersive. That means you're making error in this high frequency mode. But because they have a small contribution to your smooth function, so you don't see that in the physical space. However, things become more complicated if there is a discontinuity or if there's turbulence. So here I show you exactly the same problem, except the initial condition is now a car box. You can see a Gibbs phenomenon in this spectral method. And for the first order scheme, you see diffusion and a lot of noise in the central difference. This is because the spectrum now becomes flat. The spectrum of this continuity function becomes flat. So your error in this small scale actually show up in your physical space, and you see all of those noise. But actually, Jim is laughing. So I actually do a stupid thing here, because for a car-box function, the feature is localized spatially. So a smarter way to do the problem is to use AMR, adaptive mesh refinement, to only put your computational effort around the discontinuity. But I do not like for turbulence, because for the classical picture of turbulent cascade, the area actually spatially filled. So if you want to use AMR for your turbulent flow, you will AMR refining everywhere. There are really a lot of degrees of freedom in your problem, and you have to solve it until the dissipation scale, which is usually set by the viscosity here. Now we can ask how many degrees of freedom is in this problem in the whole spectrum. So if you assume the standard classical Kolmogorov spectrum, then it turns out the degrees of freedom is proportional to Reynolds number to the 9/4. However, for accretion disk, this is more complicated because it's not just homogeneous isotropic. We actually need to replace the size of the box by the scale height of the disk, because it's the standard in this model. You have turbulent eddy within the disk. And there is actually an other length scale in your problem, which is the radius of the disk. And there are other structures. Don't take this spectrum, don't take this shape too seriously. I just motivate by the Berger turbulence. But the point here is to adjust their different physics in different scale. So if we put in the actual number for, say, typical X-ray binary, it turns out the degrees of freedom is like 10 to the 27. It's extremely large, and that's the reason we cannot solve it directly. And this is the reason Jim said in this morning, if our simulation care about all the detail here, then we better go home. However, we did simulation, right? So let's take a look at the standard shearing box simulation we learned this morning. We assume periodic boundary condition in the vertical direction, so it's probably smaller than the scale height. And we didn't care about the dissipation, so let me stop here. This is the standard shearing box simulation that everybody wants, and this is just a movie showing you, how the MRI developed. Take some time for the initial goal. But once you set up, you see the channel solution, then is it running? Okay. So once you develop the channel solution, you have this turbulence fluid. It's just standard thing. This morning, this afternoon, after this talk, from mom will tell us about other kind of shearing box simulation that take into account the viscosity and resistivity. Although his simulation is compressible, let me put it here because it really capture the feature here. And Wednesday, Omar will tell us about large scale simulation, including the vertical structure. So I guess we can put it here. And there's other global simulation that you consider just and everything. So I guess I can put it here. And actually, let me show you another movie that's something I did a long time ago. And this is a MHD simulation with spectral method. And I calculate the synchronous radiation trying to model the Sagittarius star. But anyway, although most of us don't think in terms of case space, we're actually doing pretty well in this spectrum. We actually have different simulation address different scales. However, you see I put some gaps here. So the question I want to ask is, do we have anything in between to connect this simulation in different scales? And actually we do. And we have a single number called alpha, which we connect everything. Now for the dynamo friends, this is not the alpha effect, it's the sequence parameter, which is defined the ratio between the stress and the pressure, and which is actually an integration over fluctuation along the K space. So by looking at this figure, we can already tell we expect alpha will depend on the scale of our simulation. If our box is smaller, then we integrate a smaller region in this spectrum. So we expect alpha becomes smaller if our shearing box becomes smaller. Let's take a look at the simulation. This is a plot Martin and I make, but the data actually is still from Sino. So y-axis here is just alpha, and the x-axis is the scale height of the box. So let me flip this plot, so it becomes the K. And we actually see when we go to smaller and smaller scale, alpha decrease, as we expect in this simple scratch. Now, many of us are aware about the paper by Pingo, which point out the problem that alpha is too small in shearing box simulation. It's an excellent point, but it's not an issue, because shearing box are local simulation, so we want alpha to be small in the shearing box. If alpha is independent of the size of the box, then we have some problem. So actually, we are all right. So I guess at this point, everybody agree, although we don't think in K-space, we are all doing multi-scale study, and we are doing consistent thread by using alpha. However, there are so many data in this region, but we haven't taken advantage of them. So if I take King's point again, the small box gives us too small alpha. Probably we can fold them away and just do the large box. Will this work? Let's take a simple example. Say I do a large box simulation, and say in my grid scale, I have a full Vx like this. I know this is going to develop a discontinuity in finite time, so it always dissipates. And if I have a configuration like this is Vy, this is MRI unstable. So we will develop turbulence and we will dissipate. But say now we have this configuration. Now if we just use our numerical simulation cannot tell the direction which one is outside and which one is inside. Your artificial viscosity always dissipates. But MRI tells us this is stable and it should not dissipate. So we do have a problem here if we just forget about the small scale. And our dynamo friends will tell us it's worse because the small scale structure can actually inverse cascade back to large scale. So this is like what Steve said in the morning. The time when we think the small scale are not important, that's gone. We need to think about what happened right here. So we cannot forget about the small box. What can we do? We should model them. And that's what people use for, in large eddy simulation. They do analytical modeling. So the model Martin showed you this morning is an example of it. But the thing I really want to say now is we can actually use the shearing box to measure these small scale models. And that's what we call a good use of this information right here. So let's take an example. You already see this plot. This is the alpha prescription. This is simulation. And we have different models. Now, if we just have the analytical model, then we need to worry because we don't know which one is right. And there are parameters that we need to tune. So this is actually Ramesh's response to me when I first told him, if you have so many parameters, how do you know which one to pick? But the nice thing here is because we know how to do shearing box, well, actually we don't, but suppose we know how to do it, then we can do numerical experiment to measure this coefficient. Just like in hydrodynamics, we do experiment to measure viscosity and things like that. Okay, so how do we do this numerically? So we do it by so-called subgrid modeling by mean field MHD. What we do is we just take the average over some scale for the MHD equation. Martin already scared you by showing you big equations, so I will just show you a few terms here. In the Euler equation, the extra term part is the total stress, which turns out to be the correlation between the velocity fluctuation and magnetic fluctuation. And we usually model it with turbulent viscosity. Now, this piece is probably not familiar with the astrophysical people. It's called the mean field turbulent EMF, which is just like this. But this is what the dynamo people always talk about, the alpha effect and how do you call it? This is the turbulent resistivity. So what we want to do is to measure this quantity by doing local simulation. And
there are already assumptions that are hidden in even just that breakdown. It's not guaranteed that you'll be able to find self-consistently the values of those coefficients.
I agree. Actually, there are many, many ways to do average. Yeah. So.
And assumptions about the independence of fluctuation and things like that.
So one way to do this is actually, again, use numerical simulation. You do a really, really large high-resolution simulation, and then you put in different models to see how the average change your result, and you pick the best one. I agree. It depends on everything. So.
If you put this local shearing box simulations to determine the turbulent fluxes, why do you have to fit things like alpha and beta and so on? I mean, there are just immediate fluxes which you can put into a kind of a large-scale transport, which I don't think is what you do.
Well, actually, there are few responses to that. So, for example, in dynamo, I guess it's really recently people start to do shearing box. A few years ago, people still keep doing the periodic box. And how people set up the problem is to use so-called test field method. So you assume some field, and then by assuming this form of stress, you put that into your problem, and then you fit your coefficients. But I agree, if we have spectral method, if we have shearing box, then we can actually measure the whole form of this coefficient instead of doing some assumption. And that's what you see in the previous plot I showed you. That's actually not linear. We can. No. So if you can, Yeah, so that's actually one thing I'm going to. If you can do a local expansion, that's actually better than this kind of thing.
For this gravitational symmetry, why there's no increment alpha term in the stress test? Look at the three equations and not use
No, there is actually, there's a lambda effect, right?
What? This one is the alpha effect.
The lambda effect in two-dimensional.
In here,
why is it always
the way I see is because of Gaussian invariant. You can always boost yourself with the flow. That's what I think.
in comparing this against the global disk?
Mhm.
Can't do that. Why not? If it's shear.
So the shear is hidden here. Right? This is meant to model the shear.
Right. There's no increment alpha term in the first equation.
Yeah, in principle there is, and that's what I said, it's called lambda effect. And that's used to explain differential rotation of stars in the sun.
Okay, so we have a real expert here.
Okay, I'm right.
Yeah. Yeah, and just for some fun, the reason the dynamo people and Christian people don't talk until now is because Christian people always care about this term. Dynamo people always care about this. And how about the Reynolds stress? Only engineers care about that. But actually, in my global simulation, I do see a large Reynolds stress with you in the East Coast. So that may be an important thing to look at. But I won't say too much about it. So as we just learned, the shearing box is actually a good way to, it's already generalized to do, to calibrate the turbulent viscosity and alpha here. Because in a shearing box, we already have a background shear, and we have.
To be pedantic, which just bothers me to look at it. For TIJ, you actually make the right-hand side symmetric in ISJ.
Yep. I should.
I assume you do when you.
Yeah, but I just make it easy. I don't want a big long equation. Yeah. Okay, so I should replace it with a tilde.
Yeah, you want to vanish with solid body rotation, for example.
Yeah, you're right. You're right. Yeah. So what I think? Okay, so I was saying the shearing box is already set up so you can measure the turbulent viscosity and alpha because we already have the background shear and background magnetic field. We just set this up. We measure the form of T and E, and if they turns out to be linear in this thing, then we are happy. However, it's really, really tricky trying to alpha eta here because how can you do a gradient of your background magnetic field in your simulation? Like, how can you do that? What are the boundary conditions for your problem? So this is one equation. So this is the incompressible MHD equation. I put the background velocity here and background magnetic field here. Now, if we took the standard MRI setup when the gradient of the velocity is perpendicular to x, then this term vanish, and we can do the same thing for B. So there's some restriction. But with this restriction, I can throw away these terms. And then I subtract minus these two equations. I get the LCN variables. And I actually can pull out the mean C minus and C plus. And now I can apply the boundary condition with respect to this characteristic. Right. I'm not saying this is the way to go because myself is still really confused. But this do give you some hint. Maybe we can try to measure eta by doing local simulations. Okay, so this is about generalizing the shearing box. But there's another thing I want to show you. So this morning we hear about spectral method, and actually that's the numerical method I always use. And one reason spectral method is less popular in shearing box is probably because of the shearing coordinate. So say this is our computational domain. If the box shear like this, then your basis vector will shift like this. But because K is one form, so you shift the other way. So let's see. So once you shift your shearing box long enough, you want to remap your coordinate. so you can reshift it again. But once you do the remapping, you will bring the incorrect wave number. you will map the incorrect wave number. So, so this is really dangerous. It will give you a problem. And one way to solve this is just to keep track the wave number that you can always resolve. But then if you just do a simple calculation, you will be able to show if you do that, then you actually waste a lot of resolutions. So we should come up with a better way to do Fourier transform for a shearing coordinate so we can do better statistics. And actually, there is a better way. So there are 16 copies of the same box here, but they are actually sheared. So now you can see every time you shift in this larger box, you're actually periodic. So you can apply your standard FFT here, but because you have redundancy, I won't go into the detail, it's actually a simple mathematical trick. Then you will find out there are many terms vanish in your frequency space. So that means you can put in really few, how do you say it? You can put in really few extra computation, then you can do the shearing Fourier transform. If you want, we can go into detail after this. But what I want to show you here is now we finally, based on what I just told you, you copy the box many times. We actually have a good way to do a remapping free FFT. So now we can apply Fourier transform in a shearing box. And actually, I'm now working on a special MHD code. But every time you come up with a good algorithm, somebody actually did that. So Leaf will actually had the same algorithm, but he applied it to hydrodynamic, and actually he went to Gordon for telling him how to do that. But I guess the nice thing here is not to use the remapping free FFT doing it's not putting it in one code. Instead, it's to use the remapping free FFT to do statistics for any code. So it's like Jim said in this morning, we need to do code comparison. But instead of just comparing the mean stress, the average over the whole box, we actually want to do the spectrum comparison. We want to see for different numerical methods how the small scale and large scale are different. So I actually want to do this if you're interested. And I guess I don't have too much time left, so I will tell you where we are standing. Now we go back to this sketch. There are many physics in this problem, although they are the same MHD equation. But I want you to focus at the boundary. If we want to take into account the small scale effect in the large scale, then we call it the subgrid model. But we also want to find out how the large scale tell us about the small scale. And we can call this boundary recognition. We can call this supergrid modeling, or we can call it a generalized shearing box. So my picture in my mind is something like this. So we will have a large global simulation. We don't care about small physics here. And then we measure the mean quantity here. Probably it's not Capellian. Then we go to this box, and we put in the result here. We do the simulation, and then we bring it to the other level. And we do a few iterations. Hopefully, we will converge to one answer. And finally, let me just leave this fancy slide. Yep, that's it. Thanks for your attention.
I didn't fully understand your remap-free FFT.
Yeah, I know. I didn't have enough time to prepare. So.
Remapping does something physical. It expresses the transfer of energy to unresolved scales that should become away. It should be lost.
Yeah, actually, we want the loss. The devil is when you do the shearing and do the remapping, you do not chop that off. then that will give you the problem. But if you keep doing your standard shearing coordinate, then what happens is you can only trust the mode that you always resolve. You can always trust this part. So if your box becomes really, really long, then you throw away many, many degrees of freedom. So you waste your resolution.
How do you get around that?
The way is to, the physical picture is just to copy the box many, many times. So it's always periodic.
Allow you to be remapped frequently.
Yeah, because every time every time you need to do your FFT, you are periodic in all the directions. But it turns out, although it seems you need to copy it many times, but there is mathematical trick that you only need to do it once. Actually, this is a nice mathematical problem, and if you want to know the detail, you can wait for our paper. Or
Does this still allow for transfer of energy to unresolved scales? Is there still a numerical dissipation that goes on here as it should?
so if you do the two-third padding, then you get rid of the thing you don't want.
If you what?
You do the convolution correctly, then you get rid of the stuff you don't want.
No, I think you have explicitly two coefficients you want this to work. Because your weight numbers have to remap while the amplitude.
So what I'm saying here is, with this algorithm, you actually don't need to remap any time. You always resolve the same spectral space.
Yeah, but what I mean is that you need explicit feeding coefficients. Otherwise, your energy will be coming back from small scale to large scale.
You have an aliasing problem.
Well, unless it depends on
You can take care of that by some padding, by some zero padding in your spectral space.
But they come, there's no feedings which is just going to come back.
well, but there's aliasing being done,
Oh, yeah.
and they will have zero amplitude anyway.
Okay.
Yeah, but I agree this is pretty messy. I'm writing this code, but I still have problem with that I don't understand. But I guess the main point here is it's not for one algorithm. It's for comparison. You can use any grid basic code, apply this FFT, and you get a spectrum. And then we can compare that. I think this is the big deal here.
You should talk to him. He has a code that he can translate.
That's great. I want some expert in spectral method who tell me where's my problem. Yeah, we should talk about this.